Oh, that was fun.
All right.
Yeah, you got like rates.
Pass.
So do lose one mark on the rates one,
I was confident in the right one.
and one on.
That's better than
Yeah, that's what we worked out.
Expanded wrong.
Yeah.
Yeah, that's
All right. Related rate.
Oh, right there.
Expanded wrong.
That should be taken. Oh, that sucks. Because you had the right formula.
well done, well.
Thanks.
Do you need these back? We'll take them.
All right. Related rates. So in real life, we might not easily be able to measure the thing we want, but we can measure something related to it more easily. So for example, we might be able to say volume might be difficult to measure, but we can measure the radius more easily. So something connected or related to it. All right. So first of all, a note. When we talk about a rate of change, so a rate of change first of all, when you read rate of change, it means it is the derivative. So what rate is the volume changing, blah, blah, blah. So then it's talking about the rate of change, then that would be the derivative. And often it's related with respect to time. These kinds of questions. So what we do is we effectively use the chain rule. So we use chain rule. In the form. Alright, so seeing as I've mentioned about time, so if we want to know what dy dt is, so the rate of change of y with respect to time, then the other quantity that it might be related to, say u for example, y du times du dt. And so we want to find out how y varies with time, changes with time, the rate of change with time. Hard for us to directly measure that, but we can measure more easily another quantity, and so we use that one. So here's an example. So the example might be if we want to know the rate of change of the volume of a sphere, for example. and that's V equals 4/3 by R cubed. So it might be difficult to directly measure how this volume changes with time, but the radius might be more easily measured. So it's difficult to directly measure the volume. Or the rate of change of the volume. Which is dV dt. But we can more easily, excuse me, measure the rate of change of the radius. Change in the radius with time. And seeing as the radius is related to the volume, what we then would use to get a rate of change of the volume with time is that we would split it up using the chain rule, just because we want dV dt, and both the volume and the time we've got this radius in it, so we find dV dr excuse me, from this, and then we multiply it by dr dt to find out the related rates. Alright, so let's have a look at an example with some numbers in it.
Wait, sorry, figuring out the...
I want to know how this volume of this sphere changes with time.
Yeah.
If I can do something, split it up and say it's difficult for me to actually measure that directly.
Yeah. So would we...
But I do know how the volume change, the rate of the volume changing with the radius. And so if I can measure how the radius changes with time,
Yeah. But
then I can relate those two things together.
like, would that be your answer to the question? You writing out that paragraph?
Oh, yeah. Sorry. Example
Okay.
is
Oh.
probably not a good label for it.
Alright, sorry.
It's an explanation, I suppose,
Yeah, right. I just got confused, sorry.
rather than an example. This one's an example with numbers. Right, so in this example, we've got a radius of a circular oil slick, and the radius of that is increasing, it's getting bigger. So the radius is increasing at 0.4 metres every second. And so what we might want to do is find the rate at which the area is changing. so to measure the area directly, that's going to be quite tricky to do that. In fact, what we would have to do is measure the radius and then use that to find the area. So what we then is this is what we want. So we want how the area is changing with time, and we have the radius of the oil slick is increasing, so we're having how the radius is increasing with time, and that's equal to 0.4. So to find how the area is changing with time, we use this, how the radius changes, because we know that the area is pi r squared. So we can find the derivative of the area with respect to the radius quite easily, which is 2 pi r, isn't it? And we can figure out that bit. And so then from finding those, we can then find the rate of change of the area, because it would be dA dr times dr dt. And so the ADR is 2 pi r, and the RDT is 0.4, .8 pi r, and so then at any particular radius, so for example, what is the rate of change when the radius is 50?
Rate of change of the area.
The rate of change of the area. When the radius is 50. Then we would know that the area is changing with time, and it's 0.8 times pi times 50 then. We'll stick all of that in the calculator and you get 125.66. Because its area, it's metres squared, and because the time we were talking about was seconds, metres per second up here, that's metres squared every second. All right, we can use a similar thing if we're doing parametric equations to what we did here with this related rates. So parametric equations, remember we have another third parameter, and in this case we had a third parameter, and the third parameter was time. All right, so we can use the same technique if we got parametric equations. I'll show you how we do that. So for parametric equations, alright, so I've got parametric equations, similar use of the chain rule. Will give us the gradient. So if x is some function of t, the third parameter, and y is also some function of t, then to get our gradient, which is dy dx, that would be dy dt times dt dx to get our gradient. So we differentiate each of those with respect to t and then put it together to find the gradient of the curve. So let's have a look at an example how you might do that. So x is this one. Alright, so our parametric equations could be all sorts of interesting stuff. This particular one is 2t minus log to the base e of 2t, and y in terms of t is t squared minus log to the base e of t cubed. Aren't they nice? Alright, so what do we want to do? We want to find dy dt dx dt, and hence dy dx. All right. So first of all, dy dt. So if y equals t squared minus log to the base of e of t cubed, dy dt, 2t minus that's squared, oh that's not cubed, that's squared, sorry. There. So dy dt, 2t minus what?
Minus 1 on
T squared times 2t. Alright, we'd have to use because t squared function, we have to use the chain rule. Remember shortcut of the chain rule? Shortcut of the chain rule. In this case, log is 1 over t squared, and then the other bit of the chain rule, you've got to times by the derivative of what's inside that bracket, yeah? Where are we? This one? Yeah. It is. I'm going to get to that in a minute. So what happens is this t cancels out with one of those. And so you've got 2t minus 2 on t, yeah? And then we could stick that all over one denominator of t, 2t squared minus 2. Which is going to make life easier later when we... So dx dt, so yes, we need dx dt first, right? We want dt dx. But here we've got x in terms of t. So we've got to differentiate x with respect to t and then flip it over, yeah? So if x is 2t, then the x dt, 2t becomes 2, log to the base at e, so it's 1 over that 2t, times by the derivative of what's inside the bracket, which is 2. So in this case, the 2's cancel out, leaving us with 2 minus 1 on t. Put that over common denominator. Should then be 2t minus 1 over t, I hope. Alright, so I found dx dt, and it says, and hence find dy dx. So this is what we... So dy dx is dy dt times dt dx. So we've got the dy dt bit, but we need dt dx. And so that's just simply a matter of flipping that over. So we've got 2t squared minus 2 over t times t over 2t minus 1. These t's cancel, and then we don't have much else that we can do there. 2t squared minus 2 over 2t minus 1 would be our dy dx. So if we wanted to find out what the gradient was, that's how we would find it out. Alright, then we can go, so that's our first derivative, dy dx. Well, we can go and differentiate this again. And to do that, we need the following information. Alright, so second derivative. So we've got dy dx here, which is all very well to have that, but if I want to differentiate this, there's no x in here, is there? It's only t. So I'm going to have to differentiate my dy dx. Alright, so I'm going to have to differentiate that with respect. So our second derivative, I'm going to have to differentiate my dy dx with respect to time, because time is what's in here, yeah? So I can't differentiate this with respect to x to get my second derivative, because it hasn't got x in it, it's only got t in it. So I'm going to have to differentiate that with respect to time. And I don't want time here, I want x, so then...
So that variable must be in the equation? Whatever variable you use?
Whatever variable you use is in the equation, yeah. So I'm going to have to differentiate the first derivative with respect to t, and then multiply it by dt dx. Alright, because there's no x here, there's only t. So in your book, they use this in your textbook and in other ways that you might see it. They write this bit here, they write that as y dashed. So you might see that there. So what do you need for your second derivative? So for your second derivative, well, you need dy dx. So you need dy dx, all right, which is y dash, and you need dx dt. And then you can put those things together, but not only you need bit more than dy dx, what you need to do is differentiate this. Oops. So you need to differentiate this with respect to time. All right. So for the example we just had, so for things we've already gone part of the way through it. So for our previous example, all right, we had the x was 2t minus log to the base e of 2t. We know that y was t squared minus log to the base e of t squared. We got the derivative of that before. Alright, so from that we had that dt dx was equal to t over 2t minus 1. Alright, we knew that, and we had that dy dx was equal to 2t squared minus 2 on 2 minus 1. So to get our second derivative, we need to differentiate this with respect to time, and then multiply by that one that we already have. So let's do that. And there's a bit of mucking around with that. Should have chosen a better function so I don't have to muck around so much, but anyway. Alright, so we need to differentiate with respect to time dy dx. Alright. So if we're going to do that, so dy dx 2t squared minus 2 over 2t minus 1. So u would be 2t squared minus 2, and v would be 2t minus 1. And so we've got to use the quotient rule. Yuck. So derivative of that, 4t minus 2. Derivative of that, 2.
It's not minus 2.
Huh?
There's no minus 2.
Where's minus 2? Oh, it's gone because I've differentiated. Thank you. So when I then differentiate that with respect to time, v times u dashed, yes. So 2t minus 1 times 4t, take away u, 2t squared minus 2 times v dashed, all over v squared. Correct? Yes? No? Maybe? No one's going to commit. All right. So 8t squared minus 4t squared plus 4 all over 2t minus 1 squared. A lot of mucking around here. So we've got 4t squared minus 4t plus 4. What have I done?
Slow down 2 seconds.
2t minus 1 squared. Ah, now I'll slow down.
Thanks.
Nothing useful there, is there?
Are you not expanding the brackets to the bottom if you cancel? Is it just something?
Well, I would always try to keep things factorised,
Yeah.
because then with a bit of luck something's might cancel, and it's easier if you've got to factorise it. It's easier to see what might be able to cancel.
Yeah.
But in this case, I don't think there's anything going to be able to cancel. All right. The only thing I can do then is take 4 out, and then you've got t squared minus t plus 1, and then that doesn't factorise easily at all. So leave that as it is. Okay, so now we've got the first derivative differentiated with respect to t. We already know what dt dx is from previously, and so now we've just got to multiply those things together to get the second derivative. And then there's no, oh, forgot the squared. And then there's no cancelling that's going on there, so got 4t out in front of t squared, forgot my squared there, minus t plus 1 all over 2t minus 1 cubed. And just leave it like that. How nice is that? Very nice and fancy, isn't it? Not convinced. All right, I think that's all. Yep, that's all there is to it. All right, so sometimes there can be a bit of mucking around involved, but you get there in the end. After all, this is specialist maths. We've got to do the funnest maths.